Okay, look at this example now. We have a bit complicated system here. We have a mass with a moment of inertia J1 on this axis connected to a second axis through a couple of gears, N1 and N2. Second axis is connected to a third axis by two gears, N3 and N4. We have here a spur gear connected to a rack that's a flat gear. The radius of this gear is R and has a mass moment of inertia J2. We have this axis connected to a fixed support by a damper C2, and the rack is connected to a mass which moves vertically in the X direction, connected to the ground by a spring and a damper. And here we have axis friction or damping, C3, can represent it as a damper. And I need to model this system, find the differential equation of motion of this system. First, I have three axes that rotate. So let's name these rotations. Let's call this theta 1, and here theta 2, and for the third axis theta 3. I don't know the number of degrees of freedom here. It's going to end up to be 1, but let's see how we can simplify the system. First, let me try to get rid of this gear system. I have a mass moment of inertia term here, J1. I want to move it from the source axis 1 to axis 2. From axis 1 to axis 2, so this becomes J1, and the target axis is 2, so N2 divided by N1, the source, squared. Now I've moved the inertia term here, and then I want to move it up to the third axis here, theta 3. So going from here to this axis, I'll have to multiply this whole new J term, J1 N2 divided by N1 squared. Now my target is N4 and my source is N3 all squared. Now the damper here is at the second axis, so I want to move C3 to this axis. So this is going to be C3. The target is N4. The source is N3 all squared. And finally, I have this torque that I want to move from N1 to N2 and from N3 to N4. So exactly like I did with the moment of inertia, except that the transformation for torque is not squared. So the torque here going to that axis will be torque. The target is N2 divided by the source N1, and then going from N3 to N4, the target is N4 divided by N3. So now my system is reduced to a support, a damper, a gear, a rack, spring, and here we have this new J, and we have this new friction here, and we have a torque. All these are moved to this axis, so this is C equivalent. So now my J equivalent is J1 times N2 times N4 divided by N1 times N3 all squared. The damping C equivalent is C3 times N4 divided by N3 squared, and the torque equivalent is T times N2 N4 divided by N1 N3. Now, I have this gear and rack here. I need to relate the rotation of this axis to the motion of this mass up and down. Let me look at it sideways. Here's the gear and here's the rack. If this gear rotates with an angle theta 3 in this case, and the radius is r, so if we look at the tangential velocity here, v, which is basically x dot, the motion is x, so the velocity is x dot, and in this case for a rotating body we know that the velocity is omega r, so in my case here x dot is r times theta 3 dot. Okay, so let me start with energy terms. T is equal to, now I have a J2 here and JE. Both are on the same axis connected. So actually I will use the sum of both moments of inertia. J equivalent plus J2 times theta 3 dot squared. That's the kinetic energy in these two rotating parts. And there's kinetic energy in the mass M plus 1 over 2 m x dot squared. Now I know that x dot and theta 3 dot are related, so I can represent one in terms of the other. So it's free choice. I would go with theta 3. Okay. So I have 1 over 2 J equivalent plus J2 theta 3 dot squared plus 1 over 2 m, and x dot is r squared theta 3 dot squared. So 5 finally this becomes 1 over 2 J equivalent plus J2 plus M R squared all times theta 3 dot squared. Now, that's as far as kinetic energy goes. Then we have the potential energy, and the only potential energy term that we have here is this one spring K, 1 over 2 K x squared. I'm gonna get rid of x, instead put r theta, so it's 1 over 2 K r squared theta 3 squared. The damping, the dissipation function, I have two dampers in here along the same axis, so I can simply add them up. They're damping on the same axis. CE plus C2 times theta 3 dot squared, and one last damper here, C1 plus 1 over 2 C1 X1 dot squared, and again I can get rid of, well, actually it's X, just X, can get rid of X and substitute theta 3 for X, so that becomes 1 over 2 C equivalent plus C2 theta 3 dot squared plus 1 over 2 C1, and for X dot we have R squared theta 3 dot squared, which means that this whole thing is reduced to 1 over 2 CE plus C2 plus C1 R squared, all multiplied by theta 3 dot squared. Finally, the work term. Now the work equivalent here, the torque equivalent TE is at the axis theta 3, rotates theta 3, and that's pretty much everything we have in this problem. Have all the terms, and I can substitute these terms into the equation, Lagrange equation, or knowing that I've done all this reduction, here's my equivalent, total equivalent moment of inertia, we call it JEQ, and here's the equivalent stiffness constant. I'm going to call this KEQ, and there's your equivalent damping constant CEQ, and here's my TE. So my equation of motion is going to be J equivalent theta 3 double dot plus C equivalent theta 3 dot plus K equivalent theta 3 equals T equivalent. Or if you want to make sure, just go through the whole process of starting from here, finding the Lagrange and the Lagrangian, and differentiate. You should end up with an equation that looks like this, where J equivalent is going to be where's it? Here, J1 and 2 and 4 divided by N1 and 3 all squared plus J2 plus MR squared theta 3 double dot plus C 3 N4 divided by N3 squared plus C2 plus C1 R squared theta 3 dot plus the K equivalent is right here, K R squared theta 3 equals T times N2 and 4 divided by N1 and 3. Now, this is the equation of motion in terms of the variable theta 3. You can also, if you change your mind and you want it to be in terms of x, that's fine. We know that x is r theta 3, then theta 3 is x divided by r. So you plug in x divided by r, this becomes x double dot divided by r, x dot divided by r, and here x divided by r. And the equation becomes in terms of x double dot. So you can represent the equation in terms of whichever value you think is most appropriate to your needs in this particular problem. Okay, so again, what I could have done instead of these transformations, I could have just dealt with each part at its position. For example, for kinetic energy, I could have used for the first body 1 over 2 J1 theta 1 dot square, and the next rigid body is J2 theta 3 dot square, and the last 1 over 2 mx dot square, and then go through the transformations. We know that theta 1 divided by theta 2 is going to be n2 divided by n1. So in my case here, theta 1, theta 2, n2 divided by n1, which means that theta 2 is theta 1, theta 1 times n1 divided by n2. And in this gear pair, theta 3 divided by theta 2 the number of teeth at theta 3 is 4, so, and 4, and at theta 2, the number of teeth here is n3, which means that theta 3 is theta 2 times n theta, let's do look, theta 2 times n3 divided by n4. Now theta 2 is right here. Theta 2 is theta 1, n1 divided by n2 times n3 divided by n4. So J1 theta 1 dot squared, here theta 1 is theta 3, and then n2, n4 divided by n1, n3. You can substitute for theta 1 dot, so I end up with J1 times, here's theta 1, here's theta 1 dot squared, so that term will become J1 times n2, n4 divided by n1, n3 all squared, theta 3 dot, which is exactly what we got right here, and what we got over here. So you can either start with this, set up the relation between the angles. You probably need this one and 2 to 3 and 1, 2, 3, and just write your energy terms and the dissipation function, the potential energy terms, and then select one angle. Select theta 3 and stick with theta 3, replace everything by theta 3, or choose theta 1 and get rid of all the other angles. Eventually, if you choose theta 3, you will end up with this equation of motion.